Oh, there's like some homeworks that like we haven't been talking about the topics yet.
Yeah. So there should be 3 homeworks that we're going to be talking about them today mostly. And
Oh,
there are going to be 2 online videos of those lectures that'll go more in depth as well. So like we'll be talking about the mole today, and then we'll be talking about well, continuing with balancing the chemical equations, which will go pretty fast. Chapters 7, 8, 9, and 10, and 14 are the ones that I have to cover. So today we've started a little bit of we've done chapter 8 primarily, which is balancing chemical equations. We did that at the very beginning, but we're going to go into a little more detail about like a couple of problems and stuff, how you would use nomenclature to sit there and get the chemical equation, and then how you make sure it's balanced in that regard. So I'm going to show you that today too. So today is going to be a big day, and then there are going to be a couple of lectures that are going to be recorded. You guys have lab on Friday. However, I have interviews on Friday, so I won't be able to make the lab. I will have a recording of a lab that I've done prior on there, and that'll be your last lab for this week. Actually, you know what I'm going to do is I'm going to have a lecture to replace the lab. And so then that way we've covered all the material and you guys will be prepared for your final.
oh, when's the final gonna be?
So the final has to be taken by next Friday. Not this Friday, not this coming Friday, but the 17th. So you have to take it before the 17th. And it's going to cover chapters 2 through 14.
Oh, how many questions?
I believe there is about 70 questions. You'll have about 2 hours to complete it.
2 hours?
2 hours, yeah.
Oh, are
and they're all multiple choice.
That came in the exam and in the test?
Can you repeat that, please?
Are there gonna come like questions that we have done in the test, like on the other tests?
So yes, it's going to cover everything that we've gone over. So there's a possibility that you'll get questions that we've had gone over on other exams. So it's the same material. It's, except for the last part of it. The last part of it is going to be mainly the new stuff. Okay, so when we talk about chemical formulas, and we've been talking about chemical formulas, there's a couple of things that I want to sit there and stress with you. So one of the things that I want you guys to be able to distinguish is the difference between the subscript and a coefficient. So the subscript lets us know how many atoms or how many groups of atoms that we actually have. So in the case of sodium nitrate, right? So this means that we have one sodium because it's understood that we have one sodium, right? Oops. So it's understood that we have one sodium because there's no number next to it, and it's understood to be 1. We have 1 nitrogen, and we have 3 oxygens. Okay, so go back. So when we talk about, let's say we have magnesium. Magnesium nitrate. Okay, so in the case of magnesium nitrate, we have 1 magnesium. We have 2 nitrogens. And we have 6 oxygens. So here the subscript outside the parentheses shows us that we have 2 nitrates. And the nitrates work as a single unit. They move together. So we can't look at them as separately, and so we can't use that distributive property to define them because they work as a unit. The nitrogen and the 3 oxygens work as a unit together. Does that make sense?
Yes, kind of.
Okay, so how many atoms of each element are in the formula unit of ammonium carbonate? So the first thing that we have to do is figure out the chemical formula for ammonium carbonate. You gonna help me out with that? Good morning, Sam. How are you? Okay, so what is the chemical formula for ammonium? Do you guys have your polyatomic ion table printed out? I think I showed it last week. Yep, that is correct, except for the two part. So we know that it's NH4, and we have a plus. All right. So ammonium has an NH4 plus. Okay. We know that carbonate is CO3 2 minus. So we know that we're going to need two of the ammoniums to balance out the carbonates. So chemical formula is going to be. And can you guys hear me okay? Am I talking loud enough? Okay, so our chemical formula is going to be parentheses NH4 close parentheses 2 CO3. Okay, so how many nitrogens do I have? Are you sure? Now remember, this parentheses represents everything that's on the inside, too. That is correct. So we have 2 nitrogens. How many hydrogens? 8 hydrogens. How many carbons? 1 carbon. And how many oxygens? And we have 3 oxygens. Okay? Pretty simple, straightforward, not too hard, right? So we want to make sure that when it's in parentheses, the subscript pertains to everything that's in parentheses, okay? Okay, so this gets us to the point of where we talk about molar mass and formula mass. We kind of touched on this when I did the lab last week. If you guys see the recording, I kind of talked about how you would calculate your molecular mass, or what we call the molar mass of a molecule. Now, the way it is that the way that we sit there, we define it, it's going to be the average mass of the molecules of a compound expressed in an atomic mass units. Now, what that means is that we're basically going to take every atom that we have in that compound and use the periodic table to determine the mass. Okay, so for instance, if we're doing carbon dioxide, CO2. Well, if we look on the periodic table, we know that carbon weighs 12 12.011. And we know that oxygen weighs 15.999. We also know that there's two oxygens. There's one carbon. So we want to multiply them by how many we have. So that's 31.998. And this guy is going to be 12.011. So if we add these guys together, we're going to get a total of 44.009. And that's the units for this. Because we're talking about a single compound, we would say atomic mass units. Now, if we wanted to scale up, right, we would use what we call the mole. And we'll be talking about the mole here in a second. And the units that we would use in terms of the mole would be grams per mole. We'd have the same value. Okay, so I kind of mentioned the mole earlier. I kind of mentioned it early on when we got started. Do you guys know what a dozen is, just by chance? So if I had a dozen of donuts, how many donuts do I have? 12. That's correct. So if I have a dozen of girlfriends, how many girlfriends do I have? 12. That's correct. If I have a dozen of boyfriends, how many boyfriends do I have? 12. That's correct. Okay, so we know that a dozen represents 12 always, right? So a mole is going to be kind of like a dozen. Only thing, it's going to represent a different number. It's going to represent 6.022 times 10 to the 23rd of whatever, right? So if I said I had a mole of girlfriends, I'd be broke, you know, because I have 6.022 times 10 to the 23rd girlfriends. If I had said I had a mole of kids, then that means I have 6.022 times 10 to the 23rd girlfriends. Now I want you guys to think about this. If I offered to give you $1 trillion, right? 1 trillion. Or 1 mole of pennies, which one would you want? Okay, Sam, you'd want $1 trillion? So do you think it's the same? 1 mole of pennies or $1 trillion? Okay, so let's do the math here. Okay, so we know that a trillion is going to be 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Or ten to the 12th. Okay, so that would be a trillion. Okay. A trillion sounds more appealing. Okay. So if we have 6 point, so we say go 1 mole. And I just told you that 1 mole equals 6.022 times 10 to the 23rd. And then this is pennies. You know that 1 penny or 100 pennies equal $1. So we know that if we do that math, we have 6.022 times 10 to the 21st dollars. Okay, now which one is more? 6.022 times 10 to the 21st, or 12 or 10 times 10 to the 12th dollars. So is $1 trillion more or a mole of pennies more? Okay, obviously 10 to the 21st is greater than 10 to the 12th. So it's clear that 6.022 times 10 to the 21st is going to be more money. So for me, I would always go for the moles of pennies, right? You go out like a bandit. Even if it is pennies, right? You just have somebody else count it. You have so much money, you wouldn't really lose so much, right? And even if you did, you wouldn't even notice it because you'd have so much money. Okay. So that represents a mole. Now, a mole lets us sit there and put things on a scale that we can actually work with. Because have you ever worked with a single atom? No, we can't even see a single atom visually on our own without using a microscope or a specialized microscope. So it allows us that ability to sit there and visualize what a single atom is going to look like, or work with more than a single atom. Okay. Okay, let's move on. So this is just showing you what I was talking about by calculating the mass of the compound. So let's say we were calculating the mass of ammonium nitrate. We already know the chemical formula for ammonium nitrate because we did it earlier, I believe. So we know that ammonium nitrate is going to be NH4. And then the nitrate is going to be NO3. Okay. So we have the chemical formula. So now we just need to sit there and break it down. How many nitrogens do we have? How many nitrogens do we have here? So that's 1, that's 2 nitrogens. how many hydrogens do we have? Brittany, how many hydrogens do we have?
4.
And Sam, how many oxygens do we have?
3.
Okay, so we know if we look at our periodic table, let me pull up my periodic table. So if we look at our periodic table, so we know that nitrogen weighs 14.007. Let's go ahead and put that down. We know that hydrogen weighs 1.008. And we're going to multiply that by 4 because that's how many we have. And we know that oxygen weighs 15.999. And we're going to multiply that by 3. Okay, so this guy is going to be 28.04. This is going to be 4.032. And then this guy is going to be 47.997. Then we're going to add them all together. So we add them all together. We end up with 80.043. And the units are going to be AMU or grams per mole. So if we're talking about the molar mass, it's going to be grams per mole. If we're talking about the formula mass or the molecular mass, we're going to make reference to AMU, atomic mass units. Okay. Okay. So we just talked about the mole. So 1 mole of any substance is going to be 6.022 times 10 to the 23rd. You want to remember this. This is also called Avogadro's number. Avogadro was a scientist, and he got credited for this by having his name in front of it. He wasn't the one that actually found it, but other scientists credited for it. This is also called Avogadro's constant. And a lot of people will call it avocado because the spelling kind of looks like avocado, okay? Okay, so a sample consisting of 0.25 moles of ammonia. How many molecules of ammonia is this? So the way that we would do this calculation is by using dimensional analysis. We know that we're starting off with, or our given is going to be 0.25 moles of ammonia. Chemical formula for ammonia is NH3. Then we're going to use Avogadro's number. or Avogadro's constant. So we know that 1 mole of ammonia would equal 6.022 times 10 to the 23rd molecules. Now, we don't want to mistake moles for molecules. So we're going to make sure that we write out molecules. Of ammonia. So then our moles are going to cancel out, and then we're left with just molecules of ammonia. And we should have two significant figures, so it should be 1.5 times 10 to the 23rd molecules. Oops. Of ammonia. Okay, questions? Concerns? Cash? Kool-Aid? No questions, Brittany? What about you, Samantha? Okay, we'll move on. Okay, so when we talk about molar mass, now we're taking into consideration the mole as it pertains to mass. And I told you by using the periodic table was kind of organized and based around carbon and carbon's weight. Okay, so carbon 12 is the isotope that the periodic table is based upon. And so all of our numbers are kind of using carbon as that reference, where carbon is going to be weighing 12 grams per 1 mole, or 12 atomic mass units per 1 atom of carbon. Okay, so when we talk about the mole itself, we have the weight of carbon being 12 grams per mole. Okay, now knowing that, so when we talk about molar mass pertains to moles and mass. And so it's that conversion factor that allows us to convert from, let's say, grams of a substance to moles of a substance. And so we get the units grams per mole. Okay. So when we calculate the molar mass of calcium fluoride, molar mass, of calcium fluoride, then in this case, first thing that we want to do is determine what is calcium fluoride. What is the chemical formula for calcium fluoride? So if we go through our nomenclature, calcium is Ca. We know that calcium is going to have a +2 charge. And we know that fluorine has a -1 charge when it forms an ion. So we're going to need 2 fluorines to balance out that +2 charge. So our chemical formula is going to be CaF2. So that means that we have 1 calcium and 2 fluorines for our chemical formula. So we look on our periodic table. So we look calcium weighs 40.078. Let's write that down. and we're multiplying that by 1 because we only have 1 calcium. And then fluorine weighs 18.998. And we're multiplying that by 2. So that's just going to give us that 40.078. And then that 18.2, so that's 6, 0, 0. Actually, nine. So 37.99. 6. We add these together. 1. Point. So you get 78.074. And since we're talking about molar mass, we want to put grams per mole. Okay. Okay, so let's move forward. So the thing that we want to know about a mole, 1 mole of one substance isn't going to have the same mass of 1 mole of a different substance. So like, for instance, if you have an apple and a grape, are an apple and a grape going to weigh exactly the same mass? Sam?
No.
No, it isn't, right? Because we know that an apple is so much bigger than a grape. An apple is probably going to weigh a lot more than a grape does. Okay, so that's the same thing when we look at substances. So for instance, iron weighs 55.85 grams per mole. Aluminum weighs 26.98 grams per mole. Mercury weighs 200.6 grams per mole. Now, these are all a mole of substance. They have the same number of quantity, right? So they have the same number of atoms in this case, but each of those atoms are going to weigh differently, okay? So that's like if I have 1 apple and 1 grape, it's going to weigh differently, but they're both just 1 apple and 1 grape. Does that make sense? Okay, so when we talk about the mole, we're talking about quantity, the numbers that we have, where when we talk about mass, we talk about how much it weighs, okay? Okay, so we're going to be carrying out a laboratory reaction that requires 0.0360 moles of barium chloride. How many grams do we measure out? Well, the way that we would do this is we start off with what's given to us. We have our number of moles. Okay, so we have 0.0360 moles, and we know barium chloride, barium, Ba, has a +2 charge when it forms an ion with chlorine. So then we need 2 chlorines to balance it out. Okay, so we're going to have to go to our periodic table to figure out the molar mass of barium chloride. Okay, so barium down here. Barium weighs 137. So I'm going to put this up in the corner here. And we only have one barium. And it weighs 137.33. Okay, and the chlorine, there's going to be 2 of them. And it weighs 35.45. We know that there's 2 of them. So we get 137.33. That's going to be 70.90. We add these 2 together. It's 3, 2, carry the 1.802. So 28.23 grams per mole. Now, when we use that term, grams per mole, all that means is this is the number of grams per 1 mole of substance. So we can actually use that as an equivalency or a conversion factor. So we'll have 208.23 grams of barium chloride over 1 mole of barium chloride. Okay, so moles are going to cancel out. And then we're left with just grams. So we multiply across. So things that are on top, we're just going to multiply across. Things that are on the bottom, we're going to divide it by that. So we are dividing by 1. So do that math. So we get 7. So we have 3 significant figures here. So it's going to be 7.50 grams of barium chloride. Okay. Questions? Okay, let's keep moving on. Okay, so the beauty of this is that we can go by using the number of units, or let's say molecules or atoms, we can use Avogadro's number to convert it to number of moles, right? And then we can use the number of moles to sit there and convert that to number of grams. So by using the molar mass, okay? And MM stands for molar mass, and A stands for Avogadro's number, okay? And so I can do this, and I can go one way, or I can go back the other way. And so that's the beauty of it. And so this allows us to convert from, if we're starting out with the number of atoms, to figure out how much those number of atoms will actually weigh, okay? And this is another way of showing exactly the same thing that I just talked about. So we can go from a measured macroscopic quantity to a particulate quantity, okay? And the way that we would do that is by, if we're given mass in grams, we can use molar mass to convert to moles. And then we could use moles to convert to number of particles, so quantity, okay? So an example of this is, if we have 3.2 times 10 to the 23rd molecules of sulfur tetrafluoride, well, our given is 3.2 times 10 to the 24th molecules of sulfur tetrafluoride. So that means it has one S and 4 fluorines. Okay. So we know that we could use Avogadro's number to convert to number of moles. Okay. Avogadro's number is 6.022 times 10 to the 23rd molecules. And 1 mole is going to equal that. Sulfur tetrafluoride So molecules are going to cancel out. And then that's going to give us our number of moles. But we want mass. So the way that we would go from moles to mass is by using the molar mass. So we have to calculate the molar mass of sulfur tetrafluoride. So we know there's 1 sulfur and there's 4 fluorines. Okay, so we go to the periodic table. So sulfur is 32. Point 0.06 times 1. And fluorine was 18.998 times 4. So this is just going to give us 32.06 and 4 times. So that's what? It's 2. So that's 75.992. Okay, we add this together. Get 108.052. Okay, so we're going to go ahead and use that over here to change moles to mass. So 1 mole at the bottom, SF4, and we'll have 108.052 on top, and that's grams. So we know that the unit for this is grams per mole. So those units are going to cancel out. The moles are going to cancel out. And we're going to be left with just grams. Do that math. So we end up with 570 5.7 times 10 to the second power. And that's in grams, or 570 grams of SF. Okay. Okay, so the next thing that we're going to talk about is called percent composition by mass. Okay, so percent composition by mass is just looking at the mass of the part divided by the mass of the whole. And what do I mean by that? So the mass of the part of the compound. So if we had calcium fluoride, then let's say we wanted to look at just the fluorine in the calcium fluoride. So we would just get the mass of the fluorine divided by the mass of calcium fluoride, okay? And so that's what I mean by divided the part by the whole, or the total, okay? So if we have calcium fluoride, we go to our periodic table, we know that fluorine weighs 18.998. And we know that calcium, for calcium fluoride, has 2 fluorines. So we'd add 18.998 times 2, because there's 2 of them. And we're going to be dividing that by the molar mass of calcium fluoride. So we had calcium, which weighs 40.078. We have 2 fluorines, each one weighing 18.998 times 2. So that's just 40.078 plus 37.996. We add those together, we end up with 78.04 grams per mole bottom. So then we'll have 78.074, and then we multiply that by 100. The grams per mole for each of those are going to cancel out. So this guy is going to equal 48.7% mass of fluorine and calcium fluoride. Okay, and so if we wanted to calculate how much calcium was there, all we would have to do is subtract this number by 100. So then we'd go 100 minus 48.7. And then this would give us our percent of mass of calcium, which is 51.3% calcium in calcium fluoride. Okay? Okay, because we know that when we talk about percentage, the most that we could have is 100%. And so we just deduct the other part. Okay? Okay. Okay, it says calculate the percent composition by mass of aluminum sulfate. Okay, so if we do that, we know that aluminum is Al, sulfate, and it has a 3+ charge. Sulfate is SO4 2-. Okay, so for these guys to balance out, I'm going to need 2 aluminum, and I'm going to need 3 sulfates. Okay, so now I'm going to go to my periodic table. I'm going to calculate the mass of aluminum sulfate of the total, and then I'm going to calculate the mass of just aluminum, just the sulfur, and just the oxygen. Okay, so let's go ahead and do that. Okay, so aluminum. So we have, for aluminum, we have 2 aluminums. So, and that's going to be 2 times 26.982. Here we're going to have 3 sulfurs. Okay, so then that's 3 times 32.06. And then we're going to have 12 oxygens. So that's going to be 12 times 15.999. Okay, so let's do that math. So we got 26.92. I'm going to say 982 times 2. So that's going to equal 53.964. So we have 3 times 32.06. So that's going to equal 96.18. And then we have 12 times 15.999. So that's going to equal 191.988. So we add these all together. And we're going to get plus 8 plus 3.64. So we're going to end up with 342.132 for our total. Okay, so we calculated the aluminum. So if we want to look at the aluminum, we'd have 53.964 divided by our total, which is 342.132 times 100. So then that's going to give us 15.8% for aluminum. For sulfur, it's going to be 96.18 divided by 342.132 times 100. And that's going to give us 28.1% for the sulfur. And then for the oxygen, we have 191.988 divided by 342.132 times 100. And that's 55. 55.8. Let's see. Sorry. If I could plug it into the calculator, right? That's 56.1%. Oxygen. Okay. Okay, so that's how we would calculate the percent mass of each of the different atoms that are in the aluminum sulfate. Okay. Or percent composition by mass. Okay. Okay. So if we're given a problem where we're given the percent composition by mass of, let's say in this case, this is aluminum chloride is 38.35% of chloride. So that means 38.35% of it is going to be the chloride ion. So if we wanted to calculate the mass of the aluminum chloride that is needed as a source of 50.0 milligrams of chloride. So then we're kind of setting up the equation for ourselves because we know that it's going to be part over the whole. So if that's the case, we could sit there and set up our equation, 38.35% chlorine is going to equal we know the chlorine is going to be on top, or the chloride is going to be on top, and that's going to be 50 milligrams. And then our unknown, which we're going to refer to as X, is going to be the amount milligrams of aluminum chlorate. Okay, and that's multiplied by 100. So if we solve for X, it's horrible, let's not use X, use Z. If we solve for Z, then the units would be milligrams of aluminum chlorate. It's going to equal divided by the 50.0 milligrams of chlorine divided by the percent mass. That's still multiplied by 100, so that would give us a percentage. And the way that I would get there is by what I do to one side of the equation, I got to do to the other side of the equation. So if I multiply both sides of the equation by the Z milligrams of aluminum chlorate, do the same thing over here. The Z aluminum chloride cancels out over here, and then we're left with it over here. And then if I go ahead and I divide both sides by okay, so then that's going to cancel these guys out. And then, so then I'm left with just this equation. And then I have my answer. Plugging everything in. So 3 significant figures, so I'll end up with 1.03 times 10 to the second power, and then that's milligrams of aluminum chloride. Okay, so we could basically use percent mass to sit there and calculate how much of the starting material that we actually needed. And so you guys kind of see how we can use that percent mass to do those calculations. Okay, so the next thing that I want to talk about is empirical formulas. So when we talk about the empirical formula is kind of defined as just the lowest integral ratio of atoms to each other, okay, in a compound. So the example that we give here is we have can you guys, actually you can't see my screen, sorry. Okay, good. Okay, so the next thing that we want to talk about is empirical formula. So empirical formula is going to be the lowest value of atoms to atoms. Okay, so we want the lowest energy value ratio between the two atoms. And so that is going to represent our empirical formula. So for instance, if we have C4H10, which is butane. So if we're starting out with butane, that C4H10, so we would try to find the lowest integer possible for that. So in that case, if we divide both of these by 2, we'd end up with C2H5. Okay, so that will represent the empirical formula. Okay, so let's say, for instance, we had sugar, glucose. Glucose is C6H12O6. So if we wanted to determine the empirical formula, we'd find, again, the lowest integral ratio of atoms to atoms. Okay, so if we divide all of these by 6, we'd end up with CH2O. And so that will be the empirical formula for glucose. So again, we want to try to reduce the subscript to the lowest terms possible, lowest whole terms possible. Okay, so we don't want decimal values. Okay, so the way that we would go about determining the empirical formula from, let's say, a problem is we could either use the percent mass, and we'd have to convert that mass, the percent mass, or the mass of a compound, and we'd have to convert that into number of moles. Okay, so we need to figure out a way of converting it to moles. And the way that we'd use that is by using the molar mass to do that conversion. So let me give you an example. And then once we get the number of moles, we compare the mole-to-mole ratio of those atoms to each other. And then we want to try to find the smallest possible ratio of integers between the two atoms. Okay, and then that would allow us to write the empirical formula for the compound. So let me show you what I mean by that, because it's a lot easier to see than to read on a piece of paper. Okay, so for instance, if we have a sample of a pure compound made up of just phosphorus and fluorine, where we have 1.61 grams of phosphorus and 2.98 grams of fluorine. Okay, so the first thing that we want to do is we want to convert that to moles. So we'll put our 1.61 grams of phosphorus and our 2.98 grams of fluorine. Okay, so we want to convert this guy into moles. So the mass of phosphorus is 30.974. So put that down there. And we're going to put grams on the bottom and then 1 mole on top. Since we know that it's the molar mass, we're going to divide it by the molar mass. And so then that's going to give us our moles of phosphorus. So we get 0.052. Oh, and that's moles of phosphorus. Okay, and so we're going to do the same thing with the fluorine. And we know that fluorine is 18.998. And that's grams on the bottom and 1 mole on top. Fluorine. And so we get, that's equal to 0.157 moles of fluorine. Okay, so now we have moles and moles. And so we can compare them to each other by dividing it by the lowest number of the two. So in this case, the lowest number or the smallest number is 0.520. So we divide both of these by 0.0520. And then this guy is going to give us 1 phosphorus. Okay, now we do the same thing over here. We divide it by 0.0520. And this is going to give us how much fluorine relative to that 1 phosphorus that we have. Okay, so we get 3.01. Oops. 2. Okay, now we know it has to be a whole number, and this number is close enough to 3 just to make the assumption that it's 3 because it's 0.02. So we're going to round it just perfectly to 3. So the empirical formula for this guy is going to be PF3. Okay, so that would represent the empirical formula. Okay, questions? Now, sometimes we can end up with numbers that aren't as close to a whole integer. So let's say, for instance, if we ended up with 3.2 or 3.5, we can't just round up in these cases or round down in these cases, because that probably means that you have let's see, how do I say? You have integers that aren't readily divisible by each other. Okay, and so that means that we're going to have to take in consideration. So, like for instance, if we had that earlier, we had C2H5, right? So we had an odd integer and an even integer. Okay, so that's typically what you're going to end up with cases like that. Okay, and I'll show you an example of that a little bit later. Okay, so if you get numbers like a 3.2 or a 3.5, you don't want to just round. In that case, you need to find a number that you can multiply to make that a whole number, and multiply both of those by that amount. Okay, and I'll make up a problem, or I'll find a problem in the homework assignment, so I can do that. Okay. Okay, so if we have, here's a problem where we have percent mass. Now, since we're working with percent mass, it's percent mass. So if we made the assumption that we had 100 grams of whatever we're working with, in this case, 100 grams of nicotine, then we could sit there and say, well, if we had 100 grams of nicotine, then 74.1 grams is going to be carbon. 8.64 grams is going to be hydrogen, and 17.3 grams is going to be nitrogen, right? So we're going to make the assumption that we have 100 grams of the substance that we're looking at. So let's go ahead and make that assumption. So we start off with 74.1, and I said we assume that we have 100 grams of nicotine. Okay, so then 74.1 grams is going to be carbon. 8.64 grams is going to be hydrogen, and then 17.3 grams is going to be nitrogen. Okay, so again, we go through that process. We have to convert the moles. So we use the molar mass, or the atomic mass, for carbon. So we know that carbon is 12.011 grams per 1 mole. Oops. Okay, so we want 3 sig fig, so that's 6.7 moles. Carbon. We know this guy is 1.008 grams of hydrogen, 1 mole of hydrogen. And then for nitrogen, this guy is 15.007. Okay. Okay, so then we're going to divide it by the smallest again. So once we get to moles, now we can compare moles to each other. So we want to divide it by the smallest number. So we get that one to 1, and then everything else can go on from there. So in this case, the smallest number is nitrogen, right? Which is 1.24. So we're going to divide everything by the nitrogen value. Oops. So this guy is 4.97. So again, this guy is really, 8. This guy's really, really close to 5. So just going to round it up to 5. So we have 5 carbon. So this guy is 6. So again, this guy is close enough to 7. Then this guy is 1. So then our chemical formula for this guy would be C5H7 N. And that would be the empirical formula for nicotine. Okay. Okay, so our next topic is going from, if we have the empirical formula and we've determined the empirical formula and they give us the molar mass of the actual compound, we can actually calculate what the compound is. And the way that we do that is by dividing the molar mass of the empirical formula by the molar mass of the actual compound. Okay, and I'll show you how to do that. Okay, it says a compound with the empirical formula C2H5 has a molar mass of 58.12 grams per mole. So the first thing that we want to do is find the molar mass of the empirical formula. So we have C2H5, so then we know that we have 2 carbons and we have 5 hydrogens. So 2 times 12.011, which is going to equal 24.022. And then for hydrogen, we have 5 times 1.008. So then that's going to equal 5.040. All right. Yep. So we then add those together and we end up with 29.062. That's grams per mole. So then we take this value and divide it by our empirical number. So we'll go our 58.12 grams per mole divided by 29.062 grams per mole. And this guy is going to equal approximately 2. Okay, so then we know that we can multiply the empirical formula by 2. So then we'll get C4H10. And then that would be the molecular formula for the compound. Questions? Concern? Cash? Okay. Okay, that's it for chapter 7. I said I'll give you guys an example of that problem. I'm actually going to wait for 1 second and do that while I pull up the other one. So let me pull up a question and then a compound containing only carbon, hydrogen, and oxygen is 38.8% carbon, 9.87% hydrogen. Okay, so we know hydrogen and carbon. We know that it's only containing carbon, hydrogen, and oxygen. So then how much oxygen will I have in this case? So the way I would calculate that is you know that 100% represents the whole compound. So we subtract that 58.8% of carbon minus 9.87% of hydrogen. Okay, and then that's going to give me how much oxygen I have. So let's do that math real quick. So I get 31.3% oxygen. Here's a question. Yes, thank you. Good job, Sam. Okay, so I got 31.3% oxygen. So now I know how much of each of the different components I have. Now, here I'm going to make the assumption, again, I have 100 grams of my compound. So if I have 100 grams of the compound, of my unknown compound, then that means I have 58.8 grams of carbon. I have 9.87 grams of hydrogen. And I have 31.33 grams of oxygen. Okay, so then I divide the carbon by its molar mass, which is 12.011 grams per 1 mole of carbon. So this is going to give me 48.90 moles of carbon. I divide this by its molar mass, which is 1.008 grams per 1 mole of hydrogen. This guy's going to give me 9.79 moles of hydrogen. And then I divide this, the oxygen, by its molar mass, which is 15.999 moles of oxygen. Okay. Okay, so this guy's going to give me 1.96 moles of oxygen. Okay, so if we look at the mole to mole ratio, we want to divide it by the smallest number. So if we divide it by the smallest number, the 1.996, the 1.96 is going to be our smallest number. So 1.96, 1.96, 1.96. Okay. So then this guy is going to equal 4.90 divided by 1.96. This guy's going to be 2.5. 9.79 divided by 1.96. That guy's going to be 4.99. So we could pretty much round that one up to 5. And then this guy's going to be 1. Okay. So we have 2.5. Now, we don't want to round. We want to find a number that we can multiply that 0.5 by that will make it a whole number. So we know that if we multiply 0.5 by 2, that'll make it 1. So if we multiply everything by 2, because what we do to 1, we got to do to them all. That's going to give me a whole number for this guy. Okay. So then this guy would give me 5. This guy will give me 10. And this guy would give me 2. So the empirical formula for this guy is going to be C5 H10 O2. Okay, so it's going to be B. Okay. Okay, so you guys see that. So a little quick note, things to help me remember things. So anytime that I'm working with empirical formulas, I always kind of pay attention to if there's a decimal. So if my decimal is, it ends with 0.2, then I know I can multiply that by 5, right? And that'll give me a whole number. If my decimal ends with 0.333, then, or like 0.3, then I know if I multiply that by 3, oops, If my decimal ends with 0.25, then if I multiply that by 4, if my decimal ends with 0.5, I multiply that by 2. If my decimal ends with 0.666, I multiply that by 3. If my decimal ends with 0.75, I multiply my decimal by 4. And if my decimal ends with 0.8, I multiply my decimal by 5. Okay. Does that make sense? And so usually it's going to fall within that range, you know, and so it's kind of easy to kind of remember in that regard. Okay. Okay. Okay, so let's go over chapter 8, and we're going to go over it really fast. And then there's going to be a lecture for chapters 9, 10, and 14 that you guys are going to be responsible for. That's going to be your lab. Okay, that's going to represent your lab, those 3 lectures. Okay. So let me pull up chapter 8. Okay.
Oh, I don't know if I can ask like a really quick question.
Yes, you can.
Oh, you didn't give the practice test for for exam number 3?
It should have, it went up. The practice exam did go up for exam number 3.
Oh,
Are you not seeing it?
No.
I didn't see
Yeah,
it.
let me see. Okay. So let me get back to you on that. I'll send you a message directly on that, and then I'll take a look at it, see why it's not showing. Exam 3 practice exam. Okay, I have it. Yeah, but it should have went up. It should have actually went up a while back. So I'll take a look to see what the problem is. It could be something with my modules again. So take a look at that. Okay, let's see. Okay, so let's see. What are some evidence of chemical change? Are you guys there? So if I have a chemical reaction, what are some evidence that I know that it's a chemical reaction? You guys want to take a guess?
That it can like be like on their original state again.
Okay, so if you can't get back to the original state, okay, so yeah, that's a way. So give me an example of that. So have you guys have you ever worked with, there's that glue that changes color, right? It goes from like pink to white. Is that an example of a chemical change?
Yeah, if it can like return to be pink again. Yeah,
Okay.
maybe.
Yeah, so if it can't return back to that pink, then we know that there's a chemical change. Okay, so color change is an example of a chemical reaction, right? If we form a solid, that's another example of a chemical reaction. If we form a gas, that's another example of a chemical reaction. The log burning, right? That's, in the case of the log burning, that's an example of heat being released, right? That's an example of a chemical reaction. Or just the fact that we get light from that as well, too. That's an example of a chemical reaction, right? All of those are examples of chemical reactions. So evidence of chemical reactions are color change, the formation of a solid product, the formation of a gas, the fact that either heat is absorbed or heat is released, and then in also in the case of emissions. So the experiment that we did on Friday, where we added vinegar to baking soda. If you actually touch the bottle before you added the baking soda, the bottle is like at room temperature. As soon as you add the baking soda, it starts to get colder. So that's an example of a chemical reaction. Also, we got gas forming. So we have two ways of showing that there's a chemical reaction that happened by gas forming, and then also the fact that heat in this case is being absorbed. So then it's getting colder. Okay. So here, this is an example. So we basically added permanganate. So here we dropped into permanganate into an aqueous solution. So this permanganate solution actually over time starts to fade. It actually starts changing color. It goes back to clear, okay? Because of the chemical reaction between the water and this permanganate. Yeah, sorry. Here, this is an example of silver nitrate reacting with sodium chloride solution. And so we get a precipitate forming in this case. Here, this is an example of Alka-Seltzer. When we plop Alka-Seltzer into water, we get plop, plop, fizz, fizz. All of a sudden, you get the bubble. So you're getting gas being released. So that's the formation of gas. This here is the evolution of heat and energy. So this is thermite being reacted. And so we get, or I'm sorry, this is a sparkler. So we got a sparkler. And so as a result of us putting heat into the situation, we're getting sparks coming off of it, okay? And then this is an example of light being emitted. So our glow sticks. So when we break open them, the two chemicals react. So, and then as a result of that, we get light being formed and our glow stick glows. So have you guys ever ran into a like a pole or something like that and had to use a compress, an ice compress to put on your head or something like that, where they have to break it open and stuff like that, and it gets really cold and you put it on your injury or whatever, right? So this here is heat transfer. This is an example of also a chemical reaction, right? But it also could be an example of a physical reaction because you're going from one temperature to the other, okay? Okay, so we're going to start talking about the different types of chemical reactions. At this point, you guys are very, very familiar with balancing chemical equations. And so we're going to go through that process of balancing chemical equations, but we're going to start with using the chemical names and then changing that to chemical formulas to do our chemical equations. Okay, so when we have a solid sodium added to liquid water, a reaction occurs producing hydrogen gas and sodium hydroxide solution and heat. Okay, so the way that we'd write this chemical formula is we'd start off with our sodium solid. What is the chemical formula for sodium? Just sodium metal. Any guesses? Okay, since it's a solid and it's sodium, we're going to write Na. Na represents sodium. And we're going to put parentheses, subscript S, to let us know that it's a solid. Okay, so anytime that you have a metal or it says solid, you know that you're going to use parentheses S to represent a solid. And that's going to react with water. You know that the chemical formula for water is H2O. And it says liquid water. So it's not gas. So in this case, we're going to use parentheses L to represent liquid. And then that's going to yield hydrogen gas. Anytime that we have hydrogen by itself, hydrogen gas, it's going to be H2 because we know that hydrogen is diatomic. And then we're going to put G for gas. Okay, and then we're going to get sodium and the ion hydroxide. And that's going to be a solution. So anytime you see solution, you're going to put aqueous, unless they tell you it's in some other type of solution. Okay, so that would be the chemical formula. Now, if we looked at this, we have one sodium on our reactant side. We have one sodium on our product side. We have hydrogens. We have 2 hydrogens on our reactant side and 3 hydrogens on our product side. We have 1 oxygen on our reactant side and 1 oxygen on our product side. Is this a balanced chemical equation? That's right. It's not a balanced chemical equation because they're not matching up on each side. So we want to balance that chemical equation. So the way that we would do that is we need to find a coefficient that will allow us to sit there and do it. So we need to change the coefficients in front of our compounds or our atoms, okay, or elements, okay. So in this case, if we put, say we put 2 here. So that means that we'd have 2 in front of the sodium. We'd have 2 oxygens and 4 hydrogens. So put a 2 here. That will give us 4 hydrogens. Let's go. 2, 4, and 2. And then this guy would be now 4 and 2. And then we just put a 2 here. So then this would give us a balanced chemical equation, right? Because then now we have 2 sodiums on our reactant side, 2 on our product side. We have 4 hydrogens on our reactant side, 4 hydrogens on our product side, 2 oxygens on our reactant side, 2 oxygens on our product side. Okay, that's the balanced equation. So this is what that chemical equation will be. Plus, we would also include heat, since they told us heat was generated. Now, for right now, we're going to use just the term heat. Later on, we're going to actually add on to that, okay? So then this would be a balanced chemical equation for this reaction. And you guys already know how to balance chemical equations. So you want to keep that in mind, and we don't want to lose anything that we have. So we've talked about the symbols that you use So S stands for solid, L stands for liquid, G stands for gas, and AQ stands for aqueous, or when we're talking about solutions. Okay. Okay, do's and don'ts to balance the chemical equations. We've already gone over this. You don't want to make stuff up, right? Whether it's a real thing or an imaginary thing, just to try to balance out sides. You always want to balance out the coefficients, but you need to make sure that your chemical formulas are correct. If your chemical formulas are not correct, you're not going to be able to balance it out correct. Okay? Chemical formulas have to be correct. So you want to make sure that you know how to name the chemical compound. Okay? So at the end of the day, you want to make sure that things add up on both sides, because the law of conservation says what you put in, you must get out. And that's exactly what we did here. Okay, so let's move on. Balance the equation for the reaction of solid phosphorus pentachloride with liquid water, which yielding aqueous solutions of phosphoric acid and hydrochloric acid. Okay, so solid phosphorus pentachloride. Well, I know that it's phosphorus, so it's one phosphorus. Penta means 5, so I have 5 chlorines. And I know it's a solid, so it's going to have an S. Okay. And that's going to be reacting with liquid water. Well, I know it's water, it's H2O. L representing liquid. And then that's going to yield phosphoric acid. Man, those acids. So I know that phosphoric, that means that it's that phosphate. So it has that phosphate root. And to balance out that phosphate root, I'm going to need 3 hydrogens. It's going to be PO4 because that's phosphate. Okay, Sam, I will see you. Well, I won't see you. I'll see you next week for your presentation. So you'll get an email to try to sign up for the times that you guys are able to meet. And then you guys can let me know, okay?
On Friday, we're not having the lab, right?
That's right. You're going to have two or 3 lectures. So
Okay.
to compensate for it, okay?
Okay, thank you.
No problem. Okay, so we have also hydrochloric acid, which is HCl, since it's hydro, AQ. Okay, so we want to balance out this chemical equation. We have P, we have Cl, we have H, and we have O. Okay, so on our reactant side, we have 1 phosphorus. On our product side, we have 1 phosphorus. We have 5 chlorines. We have 1 chlorine. On our reactant side, we have 2 hydrogens. And on our product side, we have 4 hydrogens. And on our reactant side, we have 1 oxygen. On our product side, we have 4 oxygens. Okay, so if we want to try to balance this guy out, I'd probably start with the oxygens, right? So if I put a coefficient of 4 in front of my water, that's going to give me 4 oxygens. That's going to give me 8 hydrogens. Okay, so but I have 4 hydrogens here. So I have 5 chlorines. So let's see if I can get those chlorines balanced. So if I put a 5 in front of the hydrochloric acid, that will give me 5 chlorines. That's going to give me 8 hydrogens. And then the phosphorus is already balanced. So now I have everything balanced. One phosphorus, 5 chlorines, 8 hydrogens, 4 oxygens, 4 oxygens. So now I have the balanced chemical equation. And that's it. But the key is, the very first important thing is to write out the chemical formulas correctly. Now, what does those chemical formulas mean, right? So if we have a balanced chemical equation and it says that we have 2 hydrogens, 2 hydrogen gas, 1 oxygen gas is going to yield 2 waters. So that basically means if we're looking at the particulate level, we literally have 2 hydrogen gas, 1 oxygen gas, and then that's going to give us 2 water molecules. Okay. Now, if we're scaling up, we could talk about a dozen. We could have 2 dozen of hydrogen gas. That means that we need 1 dozen of oxygen gas to make 2 dozen of water. Okay. So you guys already know how to balance chemical equations. You should be pretty comfortable with that. Now let's talk about the different types of reactions. So we're going to be classifying the reaction types. The first reaction that we're going to be talking about is called a synthesis or a combination reaction. Okay, synthesis reaction is basically when you have 2 compounds that you're bringing together to make a single compound or single product. So here we have A plus X is going to yield AX. Here's an example. Write the equation for the combination of solid aluminum, and gaseous oxygen to form solid aluminum oxide. So we know that aluminum is Al, and it's a solid. So we're just going to put an S plus O2, because we know gaseous oxygen is diatomic. We know our 7 diatomics, which are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And then the diatomic ion is mercury 1. Okay, so we know that this is a gas, and we're going to make aluminum oxide. So I know aluminum has a +3 charge, so I'm going to need 2 of those to balance out 3 oxygens. Okay, so now I get to balance out the chemical equation, and I know that also that this is a solid. So I'm going to put S by it. So to balance this out, I have 1 aluminum here, I have 2 over here. I have 2 oxygen here, I have 3 over here. So I know that to balance out my oxygen, I'm probably going to have to use 2 in front of here. So then I'm going to need 3 in front of here. That will give me 6 on both sides. And then I'll need a total of 4 aluminum. Okay. Okay, so the next reaction is called a decomposition reaction. The decomposition reaction is when we actually break down a compound into its individual product or individual substances, or we could break it down to multiple substances. Okay, so in this example, we're using AX yields A plus X. Okay, water decomposes into its elements when electric energy is added. So we're going to write this a chemical equation. So we have water is going to be broken down into the elements that it made of. So that's going to be hydrogen gas, which we know is H2. Say water, the liquid. plus oxygen gas, which we know is O2. Okay, so if we go through and balance this out, so I have 2 hydrogens here, I have 2 hydrogens here. I have 1 oxygen here, I have 2 oxygens here. So to balance out those oxygens, I'm gonna have to put a 2 here. So that's gonna change this number. It's gonna change this to 4, and then this to 2. So then I'm gonna have to put a 2 in front of here to balance that out. So then that gives me 4 and 2 and 2. Okay, so then now I have a balanced chemical equation. Okay. Now, some reactions are reversible. And the way that we indicate that things are reversible, or we could say that they get into equilibrium, is by putting arrows going in both directions. Often you'll see the arrows drawn like this. This here represents equilibrium, or it means that the reaction is reversible, meaning that both products can be existing at the same time, okay? Okay, so the next type of reaction that we're going to be talking about is called a single replacement reaction. So in this case, we're going to be replacing A for B, okay? So we have BX here plus A, and that's going to yield AX plus B. The way I kind of like looking at this is like replacing the old girlfriend for the new girlfriend, or the old boyfriend for the new boyfriend, right? So this type of reactions are often are oxidation reduction reactions or redox reactions as well too, okay? And so when we do this replacement, we always want to think about how we're replacing it. So like I said, we're replacing the old girlfriend from the new girlfriend. So in that case, if we're talking about a metal has to replace a metal or hydrogen, okay? Or if we're talking about a non-metal, we're talking about replacing a non-metal for a non-metal. So we could say replacing chlorine for fluorine or iodine, something like that, okay? Okay, so the reactants are always going to end up being an element and a compound, and so you're going to end up replacing a metal for a metal or a metal for hydrogen, or you're going to replace a non-metal for a non-metal. Let me give you an example. Copper reacts with a solution of silver nitrate. Write the equation for the reaction. Okay, so we know that copper, Cu, and that's going to be a solid because we know that copper is a metal. And that's going to be reacting with silver nitrate, Ag. And silver is always going to be 1 when there's no subscript around it. So, and that's going to be NO3 because we know that nitrate is a -1 charge. And that's a solution. So we know that that's going to be AQ or aqueous. And that's going to yield so when copper forms an ion, its natural form of an ion, and most transitional metals, there are exceptions, but most transitional metals' natural form are going to be 2+, okay? So we're going to have copper 2 ion forming in this case. So it's going to be copper 2 nitrate, 3. So that means we're going to need 2 of these nitrates to represent copper 2. And then we're going to get silver metal. Okay, so to balance this chemical equation out, go down here, Ag, we have 1, 1. So since nitrate is a polyatomic ion and it's traveling together, we can actually package it together in terms of how we balance it out. So we could actually use the whole nitrate as 1 unit since it's traveling in a packet, Okay, so here I would have 2 on my product side, and I'd have 1 on my reactant side. And then on my copper, I have 1 on both sides. Okay, so to balance this out, I'm going to need to put a 2 in front of the silver nitrate. Okay, so that gives me 2 silver, that gives me 2 nitrates, so my nitrates are good. My coppers are good. So then I just need to put a 2 here to balance out the silver. And then now what I put in, I got out. Okay, so, and that will be the balanced chemical equation. Our next type of reaction is going to be, oops, clear. Next type of reaction is called the double replacement reaction. I don't know if you guys are familiar with the term swingers. So when couples date other couples and they switch partners, they're considered swingers. So this is kind of like this reaction. This reaction is like a swinger reaction, where you have AX and BY. They're going to be reacting. So in this case, A is going to go with Y and B is going to go with X. Okay, so they're going to switch partners. Often you get a product formed from this. One of your products are typically going to be a precipitant or a solid. So if you see that term precipitant or precipitate, that means that when these two guys come together, something becomes a solid. Or you'll get a gas that's going to form. So this is often what you're going to happen in this situation. So this guy is called a double replacement reaction or a double displacement reaction. It's called the same thing, okay? So silver chloride precipitates when solutions of sodium chloride and sodium nitrate are combined. Okay, so then we have sodium chloride and silver nitrate combining. So that's going to be my reactants. So silver nitrate. And we know that that's a solution. So we're going to put AQ plus sodium chloride, Na, Cl, AQ. And that's going to yield, we know that this guy is a precipitant. Okay, so that means it's going to be a solid. So that's going to be silver chloride, AgCl. And then by default, we know that the sodium nitrate is also going to come together in an aqueous solution. Okay. So the next thing is to make sure that everything is balanced. So if we go Ag, Cl, we can put the nitrate together again because it's traveling as a package deal, and then Na. So we have one Ag here, one Ag on our product side, one chlorine here on our reactant side, one on our product side. We have one nitrate on our reactant side, one on our product side. We have one sodium on our reactant side and one on our product side. The next type of reaction that we're going to talk about is called a neutralization reaction. So in the case of a neutralization reaction is when you have an acid and a base that are coming together. And as a result of it, you're going to end up with so you have acid and base, you're going to end up with water and a salt being formed. Now that's if you get complete neutralization. Okay, so again, an acid is going to be defined as a hydrogen or a proton donor in this case. So the hydrogen is going to be an ion, the hydrogen ion. And then you have your salt. In this case, it could be hydrochloric. It could be a cation. And then you're going to have your metal and your hydroxide ion that are going to be together. Okay, so then as a result of that, you're going to end up with water and yours. Okay, so an example of this is, so write the chemical equation between sulfuric acid and aluminum hydroxide. Well, so sulfuric acid, we know that sulfuric, that means it has that sulfate part of it, SO4, and we know that that's 2 minus, so that means that we're going to need 2 hydrogens to balance it out. Okay, and that's going to be an aqueous solution plus aluminum hydroxide. So we know aluminum is always going to be +3 charge, so we're going to need 3 hydroxide to balance it out. Oops. There we go. 3 hydroxides to balance it out. And then we're going to end up with aluminum sulfate. So that means that we're going to need 2 aluminum and 3 sulfates to balance each other out. And we're going to end up with water, H2O. Okay. So if we do hydrogens, oxygens, aluminum, and sulfur. Okay, so if we do this, we have a total of 3 plus 2, so that's 5 hydrogens over here. And right now we have 2 hydrogens. Our oxygens, we have, that's 3, that's 7 on our reactant side. And now we have, that's 12, 13 on our product side. Aluminums, we have 1. Aluminums here, we have 2. And then sulfurs, we have 3 here and 1 here. So we'll have 1 and 3. Okay, so what we need to do to balance it out, I would actually start off with, let's say, rather than starting off with the hydrogens, because we have hydrogen here and hydrogen there, I'd probably start off with something like aluminum, because aluminum is only on one of the compounds on each side. So then if I did that, I know that I would put a 2 here to balance this guy out. So then that changes the number of oxygens and hydrogens I have. So that's 2 times 3, so that's 6 plus, so 4, so then that's a total of 10. And then that's 2 times 3, so that's 6 plus 2, so then that's 8. Okay. So again, I got my aluminums balanced out. I look at my sulfur. So what can I do to balance out my sulfur? So right now I have 3 on one side and then 1 on the other. So if I put a 3 here, that'll give me 3 sulfurs. So, but that also will change the number of oxygens that I have. So if I look at my oxygens, I have 3 times 4. So then that's 12 plus 6. So that's 12 plus 6 is 18. And then hydrogens, I have 3 times 2, that's 6, plus 3 times 2, so that's a total of 12. Okay, so now I have 12 hydrogens, 18 oxygens. Okay, so let me get my hydrogen, since this is my only source of hydrogen on this side, get that balance. So then 2 times 6 is going to equal 12. So then I end up with 12 hydrogens, 12 coming in and 12 going out. So that's checks off. And now let's look at our oxygens. We have 12 plus 6, so that's 18. So that checks off. We have 2 coming in, and then we have 2 going out. That checks off. We have 3 coming in and 3 going out. That checks off. So now I have a completely balanced chemical equation. Okay? Okay, so our last example. Our last part is just a summary. So this is a summary of all of the chemical reactions. The only thing that I want to add on to this is a combustion reaction. A combustion reaction, anytime that you have a combustion of hydrocarbon, you're going to have, let's say, CH4 plus O2. In this case, you're always going to end up with carbon dioxide and water. So anytime that you combust an organic compound, you're going to end up with carbon dioxide and water. Okay, so same thing about balancing the equation. So in this case, we'll go CHO. So right now we have 1 carbon. We have 4 hydrogens, 2 hydrogens, and we have 2 oxygens and 3 oxygens. Okay, so to balance this out, if I put a 2 in front of here, that'll give me 4 hydrogens, and that'll give me 4 oxygens. So then I'll need to put a 2 in front of here to balance out the chemical equation. Okay? And so we've already talked about a combustion reaction. You guys are very familiar. So that's all my chemical reactions. Okay, questions, concerns, cash, Kool-Aid? That's it. That's all we got for today. Your lectures, chapters, 3 lectures, 9, 10, and 4 and 14. That's a component together. Those guys are going to be on Friday. They're going to be available already, so you guys can start taking a look at them. What I recommend is just take a look at them each day, so then that way you guys get a little bit rather than getting bombarded with it one day. Okay? You guys have a good day. Okay?